antibodies. That's not the same thing as lactose intolerance.
Right.
So an allergic reaction could be hives, it could be more severe, it could be a drop in blood pressure, it could be wheezing. But what you're talking about is lactose intolerance is just diarrhea and gaseous distension. Okay. So pancreatic amylase is going to be carried by the pancreatic duct to the small intestine just the same way that pancreatic lipase would be. So carbohydrate digestion is completed within the small intestine. So we talked about lipids, we talked about carbs. What about proteins? Where does protein digestion begin? I know. Stomach. We said that the chief cells produce pepsinogen, which is activated into pepsin. And so protein digestion begins in the stomach. And so we break down proteins into polypeptides, which still need further breakdown, still need further chemical digestion. And that's going to be the role of the pancreatic enzymes. The pancreas produces another group of enzymes called either protinases, which means they act on proteins, or you can call them peptidases, which simply means that they break down peptides. Now, when these are produced by the acinar cells, they're produced in an inactive form. So one is called trypsinogen. The OGEN means that this peptide or this enzyme is inactive. Another one, for instance, is called chymotrypsinogen. Again, the OGEN is just a way of expressing the fact that it's inactive. Another one is called pro-carboxypeptidase. In this case, the way you indicate it's inactive is by putting the pro in front, prefix. So these are all peptidases produced by the pancreas, and they're going to be carried to the small intestine. Now, while they're waiting to be carried to the small intestine, you don't want them to be activated within the pancreatic duct, because then these proteases would destroy the pancreas. So they don't get activated until they reach the small intestine, the duodenum. And what happens within the duodenum is another type of brush border enzyme produced by the duodenum is called enterokinase. Okay? And once these peptidases reach the duodenum and they're exposed to enterokinase, enterokinase will cleave off part of the trypsinogen molecule, converting it to trypsin. It's now activated. Once trypsin is activated, it can then act on other trypsinogen molecules to activate them. Remember, it's a peptidase, so it can break off amino acids to then activate other molecules just like it. And in fact, it can also activate chymotrypsinogen, and it can activate pro-carboxypeptidase. In these latter cases, it would convert chymotrypsinogen to chymotrypsin. It would convert pro-carboxypeptidase to carboxypeptidase.
And that's the
Well, enterokinase begins the process simply by activating trypsin. And then trypsin can continue the process by activating both itself and the other peptidases. Okay. But it needs that it needs the enterokinase to begin the process. So we're going to take these polypeptides that come down from the stomach and start to digest them, start to break them down into smaller peptide units. Okay? If we break off individual amino acids, they get absorbed. If we form dipeptides, number, which is just a group of 2 amino acids linked together by a peptide bond, then the brush border can help. Because the brush border also produces dipeptidases that can do that final cleavage, releasing the amino acids that are immediately absorbed. Okay. Everybody with me?
Yep.
I don't know if you remember this, but amino acids have a certain formula. Amino acids, and this is a dipeptide. This is one amino acid connected to another. Here's the peptide bond. But whether we're talking about amino acid or dipeptide or a larger protein, they all have a carboxy terminal and an amino terminal. Okay? No matter how large the molecule gets, no matter how many amino acids are added, there's always going to be a carboxyl terminal and an amino terminal. And so an enzyme like carboxypeptidase is going to work at the carboxy terminal of this peptide and cleave off that amino acid. And then it'll expose another carboxy terminal that will cleave off that amino acid. Okay? So all of these different peptidases work at different peptide junctions or peptide bonds. If we look at the pancreas under the microscope, remember we said that serous glands tend to be basophilic, darker staining. These purple rounded units, because remember these are actually little cross sections through a little grape-like structure. These are the exocrine glands of the pancreas. Whereas these lighter staining groups of cells, these are the islets of Langerhans. This is just a chart that indicates the various enzymes produced by the different tissues. Salivary glands, salivary amylase, gastric enzymes are pepsin and gastric lipase. I'm not going to ask you about the nucleases, but you get the idea. Just a nice summary. Okay. Let's talk now about the large intestine. Now, the large intestine is made up of several components. We said the part that the blind pouch that extends below the junction with the ileum, this is called the cecum. And hanging from the cecum is the vermiform appendix. Vermiform simply means worm-like. Okay. If we go in the other direction, above the ileocecal valve, which you see right here, then we enter into the colon. And the colon has various regions. This part that ascends toward the liver is called the ascending colon. Now, notice when the ascending colon reaches a point just below the liver, it takes a 90-degree turn. This 90-degree turn is either called the hepatic flexure, or some people call it the right colic flexure. Most people call it the hepatic flexure. That's the term I prefer. Now, once it turns, it becomes the transverse colon. So once it makes that 90-degree turn, it transitions from the ascending to the transverse colon. The transverse colon is then going to travel to a point just below the spleen and make a 90-degree turn. That junction is called the splenic flexure, or turns. Some people call it the left colic flexure, but the splenic flexure is a term that's more commonly used. At that point, the transverse colon becomes the descending colon. Now, when the descending colon reaches the upper part of the pelvis, it takes on an S-shaped configuration like this and becomes the sigmoid colon. Within the true pelvic cavity, the sigmoid colon transitions into the rectum, the straight part. The terminal part of the rectum is called the anal canal. Okay, that opens up to the outside. So those are all the parts of the large intestine. The large intestine is lined by a simple columnar epithelium. Okay, until you reach the anal canal. Within the anal canal, the epithelium transitions into thoracic way. One way of differentiating the large intestine from the small intestine is grossly it has a larger diameter. So grossly it has a larger diameter than the small intestine. And the other thing is that along the length of the large intestine, you see it's subdivided into little sacs. Each one of these is called a haustrum. So it's more segmented. Plural would be haustri. Haustri. Colon. Okay. I'm sorry. It would be K. Haustra. I'm saying that's something wrong with what I'm saying. Haustra. This is singular, so A would be plural. Austracoli. So that's these little series of saculations that you're seeing here. Okay, so that's a second feature that differentiates the large intestine from the small intestine. Another feature is these little sacs derived from the visceral pleura that hang off. They're filled with fat. So these little sacs going back are called epiploic. L-O-I-C appendages. And these epiploic appendages are present along the outer surface of the colon, but not the small intestine. Okay? So Haustra-coli, epiploic appendages. And there's a third modification that's not present in the small intestine. Remember that one of the outer layers of the wall is called the muscularis externa, and the typical pattern is an inner circular layer and an outer longitudinal. Well, in the colon, in the large intestine, that outer longitudinal layer does not completely envelop or encircle the colon. Instead, it's divided into 3 bands, each of which looks like this. So it doesn't completely surround, it just forms 3 bands at intervals around the colon. These bands of longitudinal smooth muscle are called tinea coli. Tinea coli. So these are 3 features that are unique to the large intestine that help to differentiate it from the small intestine. Okay, Haustra coli, epiploic appendages, and tinea coli. It's got a large diameter, right? I should also say that the ascending colon and the descending colon are peritoneal in location. Okay. But the transverse colon juts forward into the peritoneal cavity. So the transverse colon is intraperitoneal. And look here, so is the sigmoid colon. This is mesentery here. So the sigmoid colon is also intraperitoneal. The rectum is extraperitoneal. In other words, the rectum sits below the peritoneal cavity. So it's not only outside of it, but it's not behind, it's below. A mesentery that extends out to a segment of the colon is called a mesocolon. So we call the mesentery that tethers the transverse colon to the primal peritoneum, we call this a transverse mesocolon, whereas the mesentery that tethers the sigmoid colon would be called a sigmoid mesocolon. Now, you know that until you reach the anus, the epithelium is simple columnar. What's different about the large intestine versus the small intestine is that there's an abundance of goblet cells. Almost every cell is a goblet cell. So whereas in the small intestine you see scattered goblet cells, they become much more abundant in the large intestine. One of the jobs of the large intestine is to lubricate the fecal matter, okay? So to ease its passage out of the body. When you transition from small intestine to large intestine, and when I say large intestine, I'm including the cecum and the appendix, you'll lose villi. You no longer see villi, those little finger-like extensions of the lumen, okay? You continue to see intestinal glands, but they tend to be shorter and straighter.